Hello, my name is Kevin, and this is Lab Group 3B. We're doing lab number 5 today, which is all about spherical aberration. So we wanted to measure the spherical aberration of this test lens. In order to do that, we started with a laser aligned along this rail using a method, the pinhole method that we've done in previous labs, which is then reflected off a mirror and perfectly aligned along this other perpendicular rail, also using the pinhole method. So then we have our test lens and a microscope, which are both aligned using methods, again, in previous labs. And then in between the mirror and the test lens, we have a Hartmann screen, which is basically composed of 11 different pinhole apertures. And this mirror here is set up on a translation stage, a linear translation stage, which allows us to select which hole it can go through, and preferably only one at a time. And this allows us to send the beam through a certain part of the lens, so we can measure the spherical aberration at only that part of the lens at one time. And we also set up the Hartmann screen and the test lens both on linear translation stages, set up perpendicular to the rail. But in retrospect, we really shouldn't have done that. We should have just set it up directly on the rail slides, because that would have preserved the center orientation with respect to this rail here. And so we had a little bit of difficulty in aligning in the lab because of that, but we learned something from it, and we won't make the same mistake again. Pause. I'm Greg. For part C of the lab, we were told to translate the mirror to have the beam propagate through the leftmost and rightmost holes on the Hartmann disc. And these two beams represent the marginal rays of the system. And what we'd like to see is those two beams coming to focus at the exact same points. And we got them in focus by translating the microscope along this optical axis. What we instead saw was that the two focus points were 14 microns apart, and again, that's probably coming back to what Kevin said about the centering of the Hartmann disc with relation to the lens. To better illustrate the idea of marginal rays coming to focus, right now we have the microscope at marginal focus, and we are at an extreme point, and as we move through, as we translate the mirror, we can see spherical aberration is causing the other rays to be focused off axis, and this is our center. And then as we continue to translate through, we'll move further away and then back towards the other extreme point. So when we had the microscope at marginal focus, we were told to generate a ray fan plot. We did so by translating the mirror again, getting light to go through all the holes of the Hartmann disc, and then recorded the distance required in the transverse direction of the microscope to get the beam in focus. And as you can see, we generated a ray fan plot that does indicate spherical aberration, and you can tell we're at marginal focus because the extreme points tend towards 0.
So in part A, we basically do the same with part D, but instead of transverse, we measure the longitudinal aberrations, and this is a plot which we can see. And if you look at that, it's really similar to it's parabolic, and I will explain why later. And this is when we flip the lens around and we see that it has spherical aberrations, and the amount of spherical aberration is much bigger than the one with the optimum configurations. Go. And now I will explain more about why we got those results. So we start with the original equation for the aberration for spherical aberrations. So we take the derivative. What you're going to see is the cubic function right here. That explains why we have a cubic function. And because we have some defocus, that's why we have the slope at the origin. The transverse aberration can be calculated by using the formula and evaluate at yb equals 1. The longitudinal can be calculated by using similar triangles, and what we're going to see here is the parabola. That's explain why we had parabola in our experiment, and the maximum can be substituted when you put the value for your maximum W, epsilon yn. W040 can be calculated by using the equations provided in the node. And after we run through the calculation, we know that the optimum B has to be equals around 0.7. So this configuration should be better than this configurations.